So we have seen Prim's algorithm for the minimum cost spanning tree, which starts with a vertex or with a minimum cost edge and grows the tree gradually. The second strategy to build a minimum cost spanning tree is the one due to Kruskal. So in Kruskal's algorithm, what we do is we start with n components. So we think of each vertex as an isolated component, and then we try to combine components with the shortest edge available to us. So we process the edges in ascending order, and each time when we come across an edge, we include it. In other words, it grows the tree by merging two components, provided it doesn't create cycle. So for instance, if we have this graph, right? So if we sort the edges, then we start with the smallest edge, which is the edge 1 to 3. So this is the smallest edge because it has weight 6. So when we add this edge, we get a one component. Initially we start with 5 components, the 4 vertices 0 to 4. When we add this edge, it merges the components 1 and 3 and it gives us now 4 components. Now the next smallest edge is this one, right? So notice that unlike Prim's algorithm, so Prim's algorithm would take this tree which we had already started with and try to extend it in some direction, right? So we are not doing that. So instead what we are doing is we are saying we will build up this tree in disjoint parts. So as and when we can add a small edge, we add it. So when we add 2, 4, we create yet another component, but there is no cycle yet. So it's still potentially a tree. So now we have added 1, 3 and 2, 4. Now we add 0, 1, which is also the next smallest edge. So we get to 10. And then finally we try to add 0, 3 because 18 is the next smallest edge. But if I add 0, 3, then we get a cycle here because we've already added 1, 3 and 0, 1. So we can't add this edge. So we skip it. So we go to the next biggest edge. Next biggest edge is 20. And then when we add that, we are done, right? Because now we have connected these 5 vertices with 4 edges. So this is Kruskal's algorithm. So the idea is that instead of creating a tree from scratch and growing it as a tree all the time, you use the edges in a kind of greedy fashion. Anytime you can use a small edge, you throw it in. If you can't use an edge, you skip it. So to start with, we order the edges in ascending order because we want to start with the smallest weight edge and grow this tree by combining components. So we have a set of tree edges that we have currently used, right? And initially this set of tree edges is empty. So we don't have a tree to begin with. Now we scan the edges from the first to the last from 0 to m minus 1 and we try to add it to the tree, right? So if we try to add it to the set of tree edges, either it will create a new component by combining 2 components, or it will try to connect 2 parts which are already in the same component. So if it is going to create a loop, we skip it, loop or a cycle, otherwise we add it, right? So let's look at a more complicated graph. It's a little easier to visualize. So here are all these edges. Now we sort them, right? So when we sort them, we find that this is the smallest one because it has weight 5. Then this is the next smallest one because it has weight 6. Then we have 3 at weight 10, right? So we have these 3 edges all at weight 10. So we put them in some order. So say 0, 1, 4, 5 and 4, 6. So we are ordering them by the vertex number. Then we have this 18 weight edge, which is 0, 2, right? And then finally we have this 20 and then the 70, right? So this is the order of edges that we are going to process in ascending order of weight. So initially our tree is empty. So we can always add the smallest edge. So this is what we saw with Prim's algorithm also, that we could always start with the smallest edge, or we could start there with any vertex and pick its smallest neighboring edge. So here we can always start with the smallest edge because, right, to begin with everything is an isolated component. So the first edge will merely merge 2 vertices into a single component with 2 vertices. So after I do this, now I go to the next smallest edge, which is this one, right? And notice that this is going to create another component far away which has no problem, so we add that. Now we look at 0, 1, so that's this one, right? So when we add 0, 1, again it doesn't create any problem, so we add it. Now we look at 4, 5, this is our next one. So 4, 5 is going to be this edge, so again we can add it without a problem. Now we look at 1, 4, we look at 4, 6, right? Now if you look at 4, 6, the problem is that we already have these 2 edges, right? So 4, 6 if we add, it's going to create a cycle, so we have to skip it. So we skip over 4, 6, doing nothing, right? And now we look at the next one, which is going to be 0, 2, because we moved from 10 and the next smallest in the ascending order, the next is 18. Again we have a problem because we have already added these two edges, so we cannot add that edge. So we will have to skip 0, 2 as well. Okay. So we have skipped these two edges 4, 6 and 0, 2. Now we find 1, 4 is our next possible edge, and adding that does not create a cycle, so we add it. And finally we have only one edge left, which is this 2, 3, the largest edge, but that is the only edge which connects to 3. So eventually it makes sense, it has to be in the spanning tree. So we add it and we are done. Right. So this is how Kruskal's algorithm works. So the correctness of Kruskal's algorithm follows from the same observation that we used to justify Prim's algorithm. So remember, we had this minimum separator lemma. So we said that if you take the set of vertices V, right, and you partition it in any way as U and W, right. Now you take any edge which crosses this of minimum cost. So this is the smallest edge which crosses this boundary between U and W. Then the minimum separator lemma said that no matter what minimum cost spanning tree you construct, this particular edge E must belong to that tree. Right? And the argument that we said was, if it was not in the tree, then there must be some other way which connects U to W, and we could bypass that and in fact instead make the tree go through this and create a smaller tree. Right? So this was the lemma that we proved in the context of Prim's algorithm, and now we can just use the same result to claim that Kruskal's algorithm is correct. So notice that at any point the set of edges that we have create some components, and these components are disjoint, right. So initially we have all vertices separately, so these are the components. Now whenever I add an edge to my tree, some of the components get merged, but each component is different from every other component. There is no vertex which belongs to two components, right. So now when we merge these two things, if they are in the same cycle, we discard the edge, but otherwise we have to combine them. So what are we doing? We are taking two different components. So we can think of the two components as a partition. We can ignore the rest of it. We can put them in one of the two partitions. So we have essentially, we are trying to add U and V, right. So U is connected to some things, V is connected to some things, but we know that these two things are disjoint because otherwise we would have a cycle when we added this edge. So we are not getting a cycle, so we are allowed to add this edge, right. And of course we have some other components sitting around somewhere, okay, which are not connected to either of these. So what we can do is we can basically think of this as some kind of a partition, saying this is my capital U and this is my capital W, right. And now clearly, because all the edges which are yet to be added are bigger than the edge that I have now. So this is the smallest edge which connects. If I had seen a smaller edge before, I would have added it. So far I have not seen any edge which connects capital U to capital W, and this is the smallest edge of that. So therefore by this minimum separator lemma, this particular edge must be there in the spanning tree, right. So we are using essentially the same formal argument as Prim's algorithm to justify that every time Kruskal's algorithm adds an edge to the tree, that edge is a valid edge to be added. So the implementation of Kruskal's algorithm is reasonably straightforward. So what we have to keep track of are the edges in my tree. So that is this tree edges, right? And we have to now keep track of two things. We have to keep track of the vertices and the edges in sorted order to process, and we have to keep track of these components. So this is something which is new compared to the other things, because we didn't have to keep these, which group of vertices are connected to each other in any of our earlier algorithms. So the first thing we do is we sort the edges. So what we do is we take the edges are of the form typically U, V, distance or weight. So what we will do is we will represent them instead as D, U, V. So we put the weight in the front because we want to sort by the weight, right? So we create this list of edges by putting in D, U, V for every edge V, D in the list associated with U. So we process the adjacency list starting vertex by starting vertex, and for every vertex in that list we just throw it in, right. Now having done this, we sort this, right, and of course this was just something which I had used to check my code. So we sort this, and now we have the list of vertices in ascending order, right. Now we just process them in that order. So we take this D, U, V in this edge list, right, and we check whether the component of U is the same as the component of V. Now initially we said that every component must be a singleton. So that we have done in this list. So whenever, while we are processing the adjacency lists, right, we are also assigning to every component, every vertex, it's a name, right. So we are creating n components 0 to n minus 1 by saying component I is I, right. So the vertex 0 belongs to component 0, the vertex, so we are naming these components. So the initial names are 0 to n minus 1, right. So each vertex belongs to a component whose name is the same as the vertex. Now what happens when I merge two vertices, right? So I have a vertex u and I have a vertex v, and these belong to some component, right? So this component over time has some name. So this is some I and this is some j, right? Because they were originally the vertices, the components which belong to vertex I and vertex j, and as we merged, we have to, so when we merge two components, we keep one of the name of one of them, right? So if component 1 merges with component 7, then we get a new component. Now we call that new component either 1 or 7, right? It doesn't matter, but we don't have to create a new name for it. So either we rename all the ones which were called 1 as 7 or all the 7s as 1. So that's basically what's happening here. So what we do is we remember the name of the component that we are at one endpoint of the edge, and for every other vertex which has that same component, we change its component to the other point. So basically everything from here is now going to get called j instead of I, right. So this is going to extend this component. So when I take two components and I merge them, if this is component I and this is component j, either I make everything in I and call it j, or I make everything in j and call it I. So what I am saying here is if the edge is going from I to j, I am going to convert everything in I to j. So that's what this loop is doing, right. So it's saying that let C be the component of the starting vertex, and for every other vertex which has the same component name, change it to be that of the target vertex. The reason that we have to save this name is because once we process u, that name will change. So that if there are vertices after u which have the same component as u, then I will not know what their component should be. So that's why I keep a copy, this small c, to remember the component name of u before I changed it, because in the process of changing it, u may change before some of the other vertices in that component, right. So this is a very straightforward thing now. Basically we process, see, initially we sort the edges by weight, right. We assign the component of each vertex to be itself, and we have an empty set of tree edges, and whenever we find an edge which spans two components, we add it to the tree, right, and we relabel the components associated with it. Now technically if you look at this initialization, right, so one thing you will see is that if I have an undirected graph, if I have UVD, I will also have VUD. So technically every edge is going to come twice in this list of edges. But remember, the first time I add an edge, it will merge the components. So if I see it again, it will just ignore it. So it's not a real problem if I keep the edges in both directions in an undirected graph in the sorted list, because the first time it will get processed in whichever direction I pick it up, and when it comes in the reverse direction, I will just ignore it, right. So this is how the algorithm works. So the main problem with this algorithm is really this loop, right. The problem is that I need to, every time I merge two components, I need to scan through all the vertices to decide which one's components change, right. So we have to merge all these vertices. There is no way to avoid this, because although we know that u is joining v, we don't know which other vertices are also connected to u. So we have to go through and explicitly make all of those vertices which are connected to u also connect to v, right. So the first step, which is sorting the edges, right, we know can be done in m log m time if we use a efficient sorting algorithm. Now it is a simple thing to observe that because m is at most n squared, right, log m is at most log of n squared, but if you know how logs work, this is the same as 2 times log of n. So this is big O of log of n, right. So log of m and log of n are really the same. When I take logs, the fact that m is n squared doesn't matter. So I can also write m log m as m log n. It doesn't really matter, and the reason it's useful to write m log n is because later on we will see that some of the complexity depends on n and not m. So sorting is m log m, which we can also think of as m log n if we wish, right. Now this outer loop runs m times, right. For every edge in my sorted list, I have to do something. But I do something only when the edge is going to contribute to the tree, right. So I actually do this part only n times or n minus 1 times, because the tree on my n vertices is going to have n minus 1 edges, right. So, most of the times this if condition is going to say the component of u is equal to the component v, and I am going to just skip over to the next edge. The only time I have to do some work on the edge is when it is actually a tree edge, and that happens n minus 1 times. But what I have to do in those n minus 1 times is to update all the components potentially which are there. It could be one, it could be a lot, but I have to scan all the vertices, and wherever I see a vertex whose component is the one getting merged, I have to update it, right. So, this is an order n scan. So, n into n minus 1 says inside this loop, even though the loop happens m times, right, there is actually an n squared amount of work being done, because n minus 1 times I am doing a scan of n vertices, right. So, this gives us an overall complexity of n squared, right. Now, n squared is not something that we would like, but this is the same problem that we faced. It is a different problem in the sense that this is not due to the data structure that we were facing with Prim's algorithm and with Dijkstra's algorithm. So, there we were getting an n squared factor because every time we had to scan all the vertices to find the minimum one to be added next, and we did not have a clever way to extract the minimum if the vertices are not in any particular sorted order. Here the problem is different. Here our problem is that when we update a component, we have to scan all the component names and update all the ones which have the same component as the one that is being merged, and we have no clever way of understanding which ones need to be merged now. So, the bottleneck is really in this naive strategy to label and merge components, right. So, remember that these components actually represent a partition of the vertices. So, a partition of a set is if I take the set and I actually break it up into disjoint subsets such that the sum of all the subsets, the union of all the subsets is the whole set, and no two sets in that partition will intersect with each other. So, we have a collection of disjoint sets. So, what we really need is some way of maintaining this collection and performing some operations on these. So, what are the operations that we need? Given one element of the whole set, right, we need to find out which partition it lies in. So, this is this find of v. This is what we call component of w here. So, component is basically telling us which is the current component in which I will find this vertex, right. So, abstractly it is a function called find. Given a vertex, it tells me the component name or the set name in the current partition that that vertex belongs to. And the more important thing, which is really the one which got us into trouble in terms of complexity, is this one, right. I need to take two vertices. I know, so I can use find to check this, right. This is the same as asking whether find of u is equal to find of v. So, if I have the function find, I can check whether or not two vertices belong to the same component by just finding the name of their components. But if they are not the same, then I need to merge them, right. So, I have to take the union of these two partitions and make it a bigger partition. So, this is the union operation, right, the usual set theoretic union operation. So, in the set theoretic union operation, I take two sets and I combine it into a bigger set containing all the elements, and since it was a partition, all these elements will come together with no duplicates, right. So, nothing is going to get overwritten or something like that. It is going to be two disjoint sets merging, and these two will remain disjoint from everything else. So, the fact that I have a partition remains. So, I have this find operation and this union operation, and this is what I need to perform efficiently in order to break this complexity block here of doing an order n scan. So, we will see that there is an efficient way to do what is called union find. This is essentially a way of maintaining disjoint sets which form a partition such that the union and the find operation together give us something which is logarithmic rather than order n. So, across operations. So, basically we want to make sure that the cost per operation is not order n. So, every union for us is technically taking order n time, because each time we need to take the union, we have to scan all the vertices. We would like it to take logarithmic time, and if that is possible, if it takes log n time, then if we do this, we will get n log n, right, and that is what we really want. So, we will see later how to do this efficient union find. So, you can think of Kruskal's algorithm as a kind of bottom-up algorithm for a minimum cost spanning tree, right. You start with all these broken bits and you try to glue them together to form a tree, right. So, you start with these n components, and then every time you can connect something by a small edge, you do so, making sure that you never create a cycle in the process. The reason that this is correct is that whenever we find an edge that we can add using this bottom-up approach, we are guaranteed at that point that it is the minimum edge connecting two disjoint partitions of the vertex set. So, from the minimum separator lemma, it will always be part of every minimum cost spanning tree, so it is legal to add that edge. Now this algorithm that we implemented turns out to have cost n squared because of this component merging problem. Right? Every time we need to merge two components, we said we have to scan through all the vertices and update the component of every vertex, because we cannot directly say, given a vertex u, which are all the other vertices in the same component as u. And we will see later how to come out of this n squared and make it m log n. Now, one thing to remember is that we have now two algorithms. So you might ask yourself, does Kruskal's algorithm give the same answer as Prim's algorithm? If not, when do they not give the same? So if the edge weights in our graph are all different, right, then you can prove using this minimum separator lemma, among other things, that the minimum cost spanning tree is unique, right? Because the Kruskal's algorithm will pick up these things. For example, if they are all different weights, you take them in sorted order. Every edge that Kruskal's algorithm adds has to be there in the tree. Right? There is no edge that Kruskal's algorithm adds that cannot be there in the tree, and there are only n-1 edges that you can add. So there are n-1 must add edges according to Kruskal. So there is only one possible tree, and Prim's algorithm finds the correct tree, so it must find the same tree. Right? But if edge weights repeat, then this is no longer true, because then it depends on the strategy. Because in both Prim's algorithm and in Kruskal's algorithm, there is a step which says extend the tree, or in this case combine components using a minimum cost edge. If there are multiple edges which are currently minimum, so in Prim's algorithm there are multiple ways to grow the tree in different directions, but each of them has the same weight. Or in Kruskal's algorithm, if there are multiple components which can be merged using the same weight edge, we have a choice of which one to do, and therefore we might actually construct different trees. So if you want to think of an example, here is a very simple example. So supposing I construct a tree, a triangle, right, which has some equal weight. So supposing I say the weight is 10, 10, 10, right, then you can see that any two edges of this will form a minimum cost spanning tree, right. I could find this as a spanning tree, I could find this as a spanning tree, and I could find this as a spanning tree. So depending on which I choose as my first minimum edge to add and which I choose as my second minimum edge to add, I could construct three different spanning trees on this triangular graph. Right? So it's not difficult to come up with examples where the choice of the minimum cost spanning tree is not the same across iterations of the algorithm, and therefore Kruskal's algorithm and Prim's algorithm may find different spanning trees. But if they are all distinct, then the minimum separator lemma will tell you there is only one. Right? So thanks to these different choices, there are different spanning trees, and in fact there are a very large number of minimum cost spanning trees. So what we have shown is how to construct one. Right? If the question is how to enumerate all the possible minimum cost spanning trees, then that could be a very large number. So that could be an expensive thing to calculate, simply because we have to enumerate a large number of things, and there is no way to enumerate a large number of things except to list them out one by one. But what we have is this kind of, as in Dijkstra's algorithm, a greedy strategy. Remember, a greedy strategy says, here is something that I think looks good, the minimum cost edge to add. Let me add it and proceed without going back and ever changing my mind. And this greedy strategy helps you to find one good solution among these various different possible solutions that exist.